Now let us discuss about the group 2 elements, that is alkaline earth metals, right? S block has two groups of elements, alkali metals and alkaline earth metals. We discussed completely about the alkali metals. Now we'll focus on the alkaline earth metals. Fine. These are the alkaline earth metals, that is beryllium, magnesium, calcium, strontium, barium and radium. And these are the electronic configurations of all these alkaline earth metals. So now we know that they have the outer electronic configuration, that is Ns2, that is they have two valence electrons, yes, and they're ionic in nature. Fine. So all the alkaline earth metals are ionic in nature, and this is how they look like, the appearance of magnesium, beryllium, etc. Fine. Now talking about the atomic and ionic radii, they are smaller than alkali metals of same period. Yes, right. We discussed that across the same period, alkali metals have the largest sizes. Yes, and they're smaller than alkali metals. Fine. And as we go down the group, the size increases. Yes, and the atomic radii increases, and hence the ionic radii also increases. These are in the same, similar to that of alkali metals. Yes, the trends. Fine. And talking about the ionization enthalpy, they have low ionization enthalpy, yes, and low due to fairly large size of the atoms, yes, and first ionization enthalpies are more than that of the group 1 elements due to their small size, but second ionization enthalpies are smaller, fine. So when we compare the ionization enthalpies between the alkali metals and the alkaline earth metals, the first ionization enthalpy of the alkaline earth metals are more than that of the alkali metals because of the small sizes compared to the alkali metals, yes, but the second ionization enthalpies are smaller, fine, and hence the ionization enthalpy decreases as we go down the group, yes. Next is the hydration enthalpy. Similar to that of alkali metals, beryllium has higher hydration enthalpy than magnesium, then comes calcium, strontium, barium, fine, etc., and larger than those of alkali metals. So the hydration enthalpies are larger when compared to that of alkali metals, and hence they are most extensively hydrated. Fine. This is about the atomic and ionic radii, ionization enthalpy, and hydration enthalpies of the alkaline earth metals. Fine. And hence the hydration enthalpy increases as we go from bottom to top. That is, they decrease as we go down the group. Fine. And next, physical properties. So these alkaline earth metals are all silvery, white, lustrous, and relatively soft but harder than alkali metals. Fine. They're silvery, white, lustrous, and they are usually soft, but they're comparatively harder when compared to the alkali metals. Fine. And the melting and boiling point of these metals are higher than the corresponding alkali metals due to the smaller sizes. Fine. They're small in size when compared to alkali metals, and hence they're little bit harder, and they have the melting and boiling points are little higher. Fine. And the trend is however not systematic. So when we talk about the trends, when we in the alkaline earth metals, the trend is not at all systematic, and we'll know about it when we discuss about the chemical properties and other trends as well. Fine. And because of the low ionization enthalpy, they are strongly electropositive in nature, yes, and the electropositive character increases down the group, yes, from beryllium to barium. Fine. This is all clear, right? There is nothing much to explain in all this. And yes, even alkaline earth metals undergo flame test. Fine. They impart color to the flame when they are introduced to the flame. Like calcium imparts brick red color to the flame, strontium imparts crimson color to the flame, and barium imparts apple green color to the flame, and the images are shown here. And again, it's the same mechanism. When they are introduced to the flame gives enough heat for the electrons in the outermost orbit to get excited, and then these electrons come back to the normal position. They emit some radiation, and hence we get all these colors, and it's characteristic to every alkali metal and alkaline earth metal. However, the electrons in the barium and magnesium are too strongly bound to the flame, are too strongly bound to the nucleus, and hence they don't get excited by the flame. Fine. Calcium, strontium and barium, they form all these colors when they're introduced to the flame, whereas beryllium and magnesium, they're too strongly bound to the nucleus and they do not get excited by the flame. So this is about the flame test, and because of all this, that is, hence they give colors when they are introduced to the flame. This can be used for detecting the elements. Fine. So next, chemical properties of the alkaline earth metals. First, we'll discuss about the reactivity towards air and water, and hence we know that they are highly reactive, right? And beryllium and magnesium are kinetically inert. Fine. Just now we discussed that this beryllium and magnesium are kind of strongly bound to the nucleus and they do not give flame test, and hence they're kinetically inert as well because they're strongly bound to the nucleus, right? And they're inert to oxygen and water because of the formation of oxide film on the surface. Fine. And powdered beryllium burns brilliantly on ignition in air to give beryllium oxide and beryllium nitride. Fine. And magnesium is more electropositive and it burns with dazzling brilliance in air to give magnesium oxide and magnesium nitrate. Hence we see that in case of beryllium and magnesium we can sort the similarities, right? They do not give flame test because they are strongly bound to the nucleus and they are chemically inert to oxygen and water, and they burn brilliantly in ignition in air to give the respective oxides and nitrites. Yes. And calcium, strontium and barium are readily attacked by air to form oxide and nitride. Fine. Apart from beryllium and magnesium, when we talk about calcium, strontium and barium, they are attacked by air. They react with air to form oxides and nitrides. Fine. And they also react with water with increasing vigor even in cold to form hydroxides. Fine. Not only they react with air to form oxides and nitrides, they react with water to form hydroxides. Fine. And talking about the chemical properties of the alkaline earth metal, then first we'll discuss about the reactivities towards dihydrogen. It's the similar thing. Alkaline earth metals react with dihydrogen and form the respective metal hydrides. Yes, under heat, under quite high temperature. Fine. And reactivity towards halogens, they react with halogens in the presence of heat and they form metallic halides. That is, usually it's ionic halides, but in case of beryllium, we'll see the other case. Fine, we'll discuss it. Fine. Now talking about the reactivity towards acid, these metals, that is alkaline earth metals, readily react with acids and form dihydrogen. Fine. They react with acids and they liberate dihydrogen gas. Fine. And reducing nature, they are strong reducing agents. Like alkali metals, even alkaline earth metals are strong reducing agent and they have large negative values of the reduction potential, but less than that of alkali metals. Fine. They have large negative values of the reduction potential, but when compared to the alkali metals, it's less. Fine. And solutions in liquid ammonia, it's the similar when compared to the alkali metals. They dissolve in liquid ammonia to form ammoniated cation and the ammoniated electron, and hence they are conducting as well. Yes, the same thing, similar discussion. And next, the general characteristics of alkaline earth metal. Fine. Talking about the oxides and hydroxides of alkaline earth metals. To metal oxide, when they react with oxygen, they give metal hydroxide. Fine. And all these oxides except beryllium oxide are basic in nature. Again, we see beryllium as being an exception in most of the cases, right? All these oxides except the beryllium oxide, they're all basic in nature and they react with water, that is the metal oxides react with water to form soluble hydroxides. Fine. That is sparingly soluble, not completely soluble. Fine. And it increases as we go down the group, and beryllium hydroxide is amphoteric in nature and it reacts with acids and alkali both. Fine. So again there's an exception in case of beryllium hydroxide. It is not basic, right? We just discussed all the oxides are basic except beryllium oxide. So this beryllium oxide is amphoteric in nature, that is it reacts with acid as well as alkali. Fine. Talking about the halides, we just discussed about the reaction of these alkali metals with halides, right? Except for beryllium halides, all the other halides are ionic in nature. Yes, beryllium forms covalent halides. Fine. Beryllium halides are essentially covalent and they are soluble in organic solvents. Yes, and they have the polarizing power as well. And this is how the structure of beryllium chloride looks like, and we can easily see the covalent bonding, right? The beryllium chloride is nothing but beryllium halide, right? Chlorine is halogen, and we can say it's not at all an ionic bond, it's a covalent bond between the beryllium and chlorine atoms. Fine. And the tendency to form hydrides, halide hydrides, generally decreases down the group. So when we talk about alkaline earth metal, the tendency to form halide hydrates, it decreases as we go down the group. Fine. This is about the oxides and hydroxides and halides of alkaline earth metals. Now talking about the salts of oxoacids, we discuss what oxoacids are, right? The acidic proton is bound to that oxygen atom which is connected to the atom which has the oxo group attached to it. Fine. So the oxo group and the hydroxyl group are both attached to the same atom. In case of oxo acids, carbonates of alkaline earth metals are insoluble in water. Fine. So talking about the oxo acid, the carbonates of these metals are insoluble in water, and all carbonates decompose to form carbon dioxide and the respective oxide. Same this we discussed in case of alkali metals as well. Yes. And the thermal stability increases with the increase in cationic sites. So the thermal stability of these alkaline earth metals, oxo acids of these alkaline earth metals increases as we go down the group. That is when the cationic size increases. Fine. And the sulfates of the alkaline earth metal are all white solids and they are stable to heat. Fine. So the sulfates of alkaline earth metals, they are all white solids and they are stable to heat. And the greater the hydration enthalpies of beryllium and magnesium ions overcome the lattice enthalpy factor, and hence they form beryllium sulfate and magnesium sulfate. So this beryllium and magnesium ions, again we see an exception and similarity between beryllium and magnesium, right? They have greater ionization enthalpies and they overcome the lattice enthalpy factor, and hence they form beryllium sulfate and magnesium sulfate. Fine. And the nitrates are formed by the dissolution of carbonates in dilute nitric acid. All of them decompose on heating to give the oxide of lithium nitrate. Oxide like lithium nitrate. Fine. So the nitrates are made by the decomposition of carbonates in dilute nitric acid, that is HNO3. Fine. And all of them decompose on heat to give the oxides like lithium nitrate, how we discussed earlier. Fine. Next, yeah, when we were discussing about lithium nitrate, we said that when they decompose, they give oxides, whereas the other alkali metals, they do not give oxides, right? They give nitrites. But all of these alkaline earth metals, they decompose on heating and give they give oxides like lithium nitrate. Fine. And the trend is that it increases down the group. Fine. So this is about the salts of oxo acids. Next, we'll talk about the anomalous properties of beryllium. Anomalous properties of beryllium. While discussing about all these properties itself, I made sure that in most of the cases, beryllium had different properties compared to the other alkaline earth metals, right? So the first one is beryllium has exceptionally small atomic size and ionic size. Yes. And they have high ionization enthalpy and small size, and because of this it forms compounds which are largely covalent, and hence they get hydrolyzed easily. Fine. Because of this small size and their high ionization enthalpy, it forms covalent compounds, and further they are soluble in organic solvents, right? And they get easily hydrolyzed. Fine. And beryllium do not exhibit coordination number more than 4. As its valence shell, there are only 4 orbitals. While other alkaline earth metals, they can have coordination number 6 by making use of the d orbitals. Fine. So the maximum coordination number beryllium can show is 4 because of the existence of only 4 orbitals. Fine. And the oxides and hydroxides of beryllium, the oxides and hydroxides of beryllium are amphoteric in nature, while the other oxides and hydroxides of the other alkaline earth metals are all basic, right? Except for beryllium, which are amphoteric in nature, that is, they react with acids and alkali as well. Fine. Next, we'll discuss about the similarities between beryllium and aluminium. Yes, while discussing about the properties, again we noted the similarities between beryllium and magnesium at many places, right? So, yeah, this is again the diagonal relationship between the beryllium and aluminium. Fine. So we'll discuss what is about it. So the ionic radius of beryllium is 31 picometer. Fine. And the charge to radius ratio is nearly the same as that of aluminium ion. Charge to radius ratio is nothing but polarizing power, right? So the ionic radius of beryllium is 31 picometer, but when we compare the charge to radius ratio of beryllium and aluminium, this is more or less same. Fine. And like aluminium, beryllium is not readily attacked by acids because of the presence of the oxide film on the surface of the metal. Yes, we discussed about this as well when we discussed about the reactivity towards air. Fine. And beryllium hydroxide dissolves in excess of alkali to give a berylate ion, just as aluminium hydroxide reacts with in the presence of excess of alkali to give aluminate ion. Fine. So then the chlorides of beryllium and aluminium have fluorine bridge chloride structure in vapor phase. We discussed about the halides, right? We saw the chlorides of beryllium, right? Even the aluminium ion have the same chlorides, that is, they are bridged structure. Fine, the chloride is bridged in the vapor phase. Fine, and both the chlorides are soluble in organic solvents and are strong Lewis acid. So beryllium chloride and aluminum chloride are strong Lewis acid. This we'll discuss when we are talking about all this, organic reactions and all. When we come across those, we see that aluminum chloride, beryllium chloride, these are all, you know, strong Lewis acid, and especially we discuss about it when we talk about Friedel-Crafts catalyst, that is Friedel-Crafts alkylation, acylation. We use Lewis acid for the reaction to proceed. Fine, so these are important in that case. Fine, and beryllium and aluminium ions have strong tendency to form complexes. Fine, so this is about the similarity between beryllium and aluminium ions. Now moving ahead, we'll talk about some important compounds of calcium. Fine. So earlier in case of alkali metals, we discussed about some important compounds of sodium, right? Here we'll discuss about the important compounds of calcium. Fine. Calcium has the atomic number 20, and it has important compounds like calcium oxide, which is also known as quicklime, that is CaO. Fine. And calcium hydroxide, also known as slake lime, that is CaOH twice. And calcium sulfate, which is very well known as plaster of Paris, right? And comes the calcium carbonate, that is CaCO3, and next is the cement. Fine. So we'll discuss about all of this one by one. So the first one is calcium oxide. Fine. So this is how the structure of calcium oxide looks like. Ca double bond O. Fine. And calcium oxide is formed from calcium carbonate, that is limestone. When it decomposes at quite high temperature, it forms calcium oxide and carbon dioxide. And further, this calcium oxide reacts with water to form calcium hydroxide, which will be the next one we'll be discussing about. Fine. And this calcium hydroxide reacts with carbon dioxide to form calcium carbonate again. Fine. And H2O. Fine. So yeah, calcium carbonate is white amorphous solid, and it has a melting point of 2870 Kelvin. It's a very high melting point. Fine. It is a white amorphous solid. And the uses of calcium oxide are, it is the cheapest form of alkali available. Fine. So, and it is very cheap, right? And it is used in the manufacture of cement. Fine. And it's used in the manufacture of sodium carbonate from caustic soda. Fine. It is used in the purification of sugar and the manufacture of dye stuffs as well. So this is about the calcium oxide, how it is prepared and the other reaction it undergoes, and the uses of calcium oxide. Fine. Next we'll talk about calcium hydroxide. While discussing about the synthesis of calcium oxide, we discussed that calcium oxide, when reacts with water, forms calcium hydroxide, right? This is how calcium hydroxide is formed, and this is how it looks like, the structure. And calcium hydroxide, on further, when it reacts with chlorine, when it reacts with the molecule of chlorine, it forms calcium oxychloride, which is a bleaching powder. Fine. Bleaching powder, we know about it, right? We use it. And the uses of calcium hydroxide, it's used in the preparation of mortar, which is a building material. Fine. All these, cement, mortar and all basically used for building, right? And it is used as whitewash due to its disinfectant nature. Calcium hydroxide is disinfectant in nature, and hence it is used as whitewash. Fine. And it is used in glass making as well, and it is used in tanning industries and for the preparation of bleaching powder, which we just discussed, and for the purification of sugar. So this is our uses of calcium hydroxide. So now we discussed about calcium oxide and calcium hydroxide. Next, calcium carbonate. So this is how the structure of calcium carbonate looks like, CaCO3. Fine. And yeah, again the same reaction. Calcium carbonate decomposed to form calcium oxide and carbon dioxide, right? Calcium carbonate is nothing but limestone, right? Quicklime. And fine. And when calcium hydroxide reacts with carbon dioxide, we get calcium carbonate again, right? And the uses of calcium carbonate are, it's used as building material in the form of marble. Fine. So we discussed about how all these calcium compounds are used for building materials, right? Cement, mortar, and in the form of marble as well. And for manufacturing of quicklime, that is how we saw, right? Calcium carbonate, that is limestone, decomposes to form calcium oxide, that is quicklime, right? And it's used as a flux in the extraction of metals such as iron. Fine. So it is used in the extraction of metals as a flux. Fine. And this calcium carbonates is used in the manufacture of high quality paper. Fine. And it's used as an antacid and mild abrasive in toothpaste as well. And it's a constituent of chewing gum and a filler in cosmetics. You can see the vast application of calcium carbonate, right? And it's a variety of applications. It's used in building material, manufacture of quicklime, and it's used as antacid, mild abrasive in toothpaste. It's used in cosmetics and a constituent of chewing gum as well, right? Chewing gum. Next, calcium sulfate. Calcium sulfate reacts with this is just the reaction formula, fine. And this is how calcium sulfate dihydride looks like, fine. It is obtained from calcium sulfate dihydride, fine. And the uses of calcium sulfate are plaster of Paris. We know how much plaster of Paris is used in building. Again, the calcium compounds are used in buildings, fine. And it's used as it's plaster of Paris. It's used in industry as well as plasters, fine. And it is immobilizing, and it's immobilizing the affected part of organ where there is a bone fracture of sprain. So when an organ is affected, that is, it has bone fracture or sprain, calcium sulfate is used for immobilizing the affected part, fine. And it is used in dentistry, in ornamental work as well, fine. And it is used for making casts of statues and busts, fine. This is about the calcium sulfate. So these are about the compounds of calcium, how they are used, their variety of applications as well, fine. Next, we'll discuss about the biological importance of magnesium and calcium. We know that our body requires magnesium and calcium as well, right? So we'll discuss about their biological importance as well. And again, a normal adult, that is an adult body, contains 25 grams of magnesium and 1200 grams of calcium. That is a very huge, right? So we know that they're very much important for us. And the daily requirement in the human being has been estimated to be 200 to 300 milligrams. Fine. Moving ahead, all enzymes that utilize ATP in phosphate transfer require magnesium as a cofactor. We were discussing that in case of phosphates, and when phosphate ions is used for the hydrolysis, oxidizing for glucose, right? Glucose oxidizes to form ATP, right? When we were discussing about phosphate ions, fine. So when glucose oxidizes to form ATP, all enzymes that utilize the ATP in the phosphate transfer requires magnesium as the cofactor, fine. So magnesium is used as a cofactor in this yeah, all the enzymes utilizing ATP in the phosphate transfer mechanism, fine. And the main pigment for the absorption of light in chlorophyll in plants, that is chlorophyll, contains magnesium. We know that chlorophyll is the pigment in the plants, right? It is responsible for the absorption of light. It gives the colors to the plant, right? It contains magnesium. Fine. About 99% of the body calcium is present in bones and teeth. We know that, right? All our bones and teeth are made up of calcium, right? And it plays important role in neuromuscular function, intraneural transmission, cell membrane integrity, and blood coagulation, etc. These are most of the important roles. And the calcium concentration in plasma is regulated at about 100 mg per liter, and it's maintained by two hormones, that is calcitonin and parathyroid hormone. So these calcitonin and parathyroid hormones maintain the concentration, calcium concentration in the plasma, fine. And interestingly, that is calcium is mainly present in the bone and teeth, right? We think that bone is inert, right? It's not reactive, it doesn't corrode or anything like that, right? No, bone is not inert and it's an unchanging substance, but it is it's not inert and not unchanging, but it is continuously being solubilized, and it is redeposited to an extent of 400 mg per day in any man. So this is something we believed, right? We were thinking of, right? We were thinking that bone is inert and it's basically unchanging, but no, it is continuously being solubilized, and it is redeposited to an extent of 400 mg per day in a man, fine. And all this calcium passes through the plasma. So this is about the biological importance of magnesium and calcium. So this is about the alkaline earth metal. So now we have a basic idea about the alkali metals and the alkaline earth metals as well. So this is all about the S block elements. And thank you for watching. And if you are liking these videos, please don't forget to like, share and subscribe to read my course. Thank you.